Let's wait for 5 minutes so that people can join. So I hope you people have watched the lecture videos. Today we'll be solving some problems related to the adjoint of an operator and weak topology. So firstly, let's recall what do we mean by adjoint. Suppose V and W are two Banach spaces. T is a linear operator from V to W, continuous linear operator. We define its adjoint T star from W star, where W star is the dual space of W, to V star, such that T star G is equal to at any point V, because T star G is an element in V star, so it is a functional defined on V. T star G at any point V is given by G at TV. Now, since TV is in W and G is in W star. So this is how we define adjoint. So let's do some problems related to the adjoint of an operator. Mainly they are basic properties that we will be proving. If T and T star are injective, that means one-to-one map, injective, and range T is closed. Show that T must be invertible. So in order to prove that T is invertible, we need T to be 1, 1 and onto. That means if we prove that T is surjective, we are done. Solution. To show that T is invertible, we need T to be surjective, because already it's given to be injective. That means we need to show that range T. Okay, so they're starting. We assume that T belongs to LVW. So we need to show that range T is equal to W. Now suppose range T closure, which is equal to range T itself, is not equal to W. This implies there exists some vector W which belongs to space W minus closure of range T. Now, by Hanbanach theorem, since range T is a subspace of W, we can find by Hanbanach theorem we can find a functional G in W star such that its restriction on range T is equal to 0 and G at this W is equal to 1. This implies T star G at any V is equal to G at TV. Now since G is 0 on range T and TV belongs to range T, this is equal to 0 for every V in V. This implies T star G is equal to 0. That means G belongs to kernel T star. Now since we are given that T star is injective, that means kernel T star is singleton 0. This implies that G should be trivially 0. But we had taken G to be a non-zero functional, which is it gives us a contradiction. Therefore, range T should be equal to the space W, which implies T is surjective and hence invertible. I hope this solution is fine with everyone. Let's move to next part. B. Show that T star need not be surjective if T is injective. That means we need to show that there exists a T such that T is injective or 1 1, but T star is not onto. So let's see how we can find such T. Taking V and W to be equal to L2 space. Now define T from L2 to L2 such that T of x1, x2, so on is equal to x1 by 1, x2 by 2 square, x3 by 3 square, and so on for every x equals to x1, x2, so on in L2. Now we'll show that this T1, this T is injective, but still T star is not surjective. Firstly, let x and y in L2 be such that Tx equals to Ty. This directly implies that xi by I square is equal to yi by I square for every I, which implies clearly xi equals to yi for every I. Therefore, so this implies T is injective. Now suppose if T star is onto. If possible, T star is onto. This implies now T star is a map from W star to V star. So in our case, W star and V star are both L2 star, and we know that L2 star is L2 itself. So this implies for F equals to 1, 1 by 2, 1 by 3, so on. Clearly this belongs to L2 and this defines a map. So by F we mean F from L2 to R. F of x is summation k from 1 to infinity xk by k. So for this F in L2 star, there exists some G in L2 star such that T star G is equal to F. That is T star G x is equal to Fx for every x in L2. And how is T star G defined? This is G of Tx is equal to f of x for every x in L2. Now suppose if G was defined by the sequence G1, G2 and so on, this implies summation k from 1 to infinity Gi, Gk Txk. This is equal to summation k from 1 to infinity f of x. So this is 1 by xk by k. And how is Tx defined? So Txk is basically xk by k square. So this implies summation k from 1 to infinity gk xk by k square is equal to summation k from 1 to infinity xk by k. For every x equals to x1, x2, so on in L2. Now, since En is sequence such that 0, 0, it is 1 at nth position and 0 else, this belongs to L2 for every n in N. This implies summation k from 1 to infinity. In fact, this will be just, okay, let me write gk enk by k square is equal to summation k from 1 to infinity enk by k. Now, since en is 0 everywhere except for k equals to n, the sum is gn 1 by n square is equal to 1 by n. This implies gn is equal to n. Now, this happens for every n in n, for every n in n. This implies g is 1, 2, so on. But clearly, this does not belong to L2. Now, this gives us a contradiction because we started with G in L2 star, which is obviously L2. Therefore, we get a contradiction. And hence, T star is not surjective. So basically, we found an example of T being injective, but T star is not surjective. I hope this proof is fine with everyone. Okay, let's move to next question. Number 2. Let V and W be two Banach spaces. A is a map defined on domain of A, which is a subset of V to W. Be closed and densely defined. That means the map is closed, and this dA closure is basically equal to V, and using this density we can extend this A to whole V. Part A. If range of A is dense, then show that A star is injective. Solution. Since we are given that range A is dense, that means we have range A closure. This is whole space W. Now suppose G1 and G2 defined on domain of A star. Since here domain of A is not the whole space V, so we cannot take this to be whole V star. Sorry, whole W star. This is a subset of W star. Be such that A star G1 is equal to A star G2. That means A star G1 at V is equal to A star G2 V for every V in V, because A star G1 and A star G2 are elements in V star. So by definition of star, this is G1 AV is equal to G2 AV for every V in V. This gives us G1 minus G2 at AV is equal to 0 for every V in V. This implies G1 minus G2 at W is equal to 0 for every W belonging to range of A. Now let W prime belongs to W minus range A. Since W is closure of range, this implies there exists a sequence Wn in range A such that Wn converges to W dash, because W is equal to range A closure. This implies G1 minus G2 at this W prime, by continuity, this is equal to G1 minus G2 limit n tending to infinity Wn. This limit can be taken outside. Limit n tending to infinity G1 minus G2 at Wn. Now, since Wn is an element in range of A, and we know that for all W in range of A, this is 0, so this is 0. Therefore, G1 minus G2 at W is equal to 0 for every W in W. This implies G1 is equal to G2. Hence, our A star is injective. I hope this proof was fine. We also have this result conversely. That means if A star is injective, in that case range of A is dense in W. If A star is injective, so that range of A is dense in W. Solution. Now suppose, so we need to prove that range A closure is equal to W. Clearly this is a subset of W. Suppose if possible, there exists some W in W minus range A closure, then as done in previous question B part, previous question A part. Yeah, here also we started with some W in W minus range T closure, and eventually we proved that this G should be trivially 0, because kernel T star was singleton 0. So basically, hmm, here also, since we are given that T star is injective, sorry, A star, since A star is injective and hence kernel A star is singleton 0, this implies, as done in first A part, there exists some G. Eventually we'll get a contradiction. We will get a contradiction. So therefore, we should have range A closure is equal to W. That means range A should be dense in W. So mainly, this is just a replication of what we did in the first question. Okay, let's move to next question. compute A star when A from L2 to L2 is given by part A maps the sequence x1, x2, so on to the sequence x1, x2 by 2, x3 by 3, and so on. Now we'll compute the adjoint. So we know that the adjoint is defined from L2 star to L2 star is such that A star f at any point x is equal to f a of x for every x in L2 and f in L2 star. Now let f belonging to L2 star be arbitrary. This implies there exists some y in L2 such that f of x is summation k from 1 to infinity yk xk for every x equals to x1, x2, so on in L2. This implies A star f at any point x, which is defined as f of ax, is equal to f of ax is given by the sequence x1, x2 by 2, x3 by 3, and so on. And f is defined as this is equal to summation k from 1 to infinity yk. And here the kth term is xk by k. For every x equals to x1, x2, so on in L2. So this implies A star f is a functional in L2 star, which is defined using the sequence y1, y2 by 2, so on. This belongs to L2 star for every f, which was basically defined by the sequence this in L2 star. Here we can see that A star f is equal to, in fact, we can say that A star is equal to A because A was mapping any sequence y1 by 2 yn to y1 by 1 y2 by 2 in this form. Here also we have similar map. So is it fine how we computed A star? Okay, let's move to next part. In this case, we define A, x1, x2, x3, so on to the sequence which has first n terms same as that of the sequence and rest of the terms are 0. So now again, suppose y belonging to L2 star is arbitrary. So by y I mean the functional defined using y. This implies A star y at any point x is y at ax, which is summation. Now, since ax has just first n terms non-zero, rest of the terms are zero. So this sum will be from 1 to n, and this is yk times xk. This implies a star y, this is for every x in L2. So a star y is basically generated by the function, by the sequence y1, y2 up to yn, rest of the terms are 0. So here also we can see that A is equal to A star. Similarly, let's see part C. Here we define A, x1, x2, so on equals to 0, x1, x2, so on. So basically we are shifting the sequence right hand side and taking first term to be 0. We'll see that the adjoint of right shift operator will be left shift operator. So let y belonging to L2 star be arbitrary. Then A star y at any x this is equal to summation k from 1 to infinity xk yk. Sorry, this is equal to y at ax. So this is summation k from 1 to infinity yk times kth term of ax. And we know that kth term of ax is actually k minus 1th term of x, except for the first term. So I can write it as summation I from 1 to infinity xi yi plus 1. So this is g of x, where g is defined from L2 to R. G of x is just left shift, because now we don't need first term of this y. Should write it as y, y2, y3, and so on. Therefore, a star y is y2, y3, y4, and so on. That means left shift operator. So I hope this is fine. Next, we'll look at some problems related to weak topology. So weak topology is basically the finest, or we can say the smallest topology under which all the functionals remain continuous. I hope you all have done in class how open balls in weak topology are defined. So we'll be using it. So let me just recall. If we have a Banach space V, then VW is the vector space V with the smallest topology called the weak topology. So we say the convergence in weak topology is given as follows. If Vn is a sequence in V, we say that Vn converges to V in weak topology, or Vn converges to V weakly if and only if Fvn converges to Fv for every f in the dual space. And if I want to define some open ball around a point x in V, then ball of radius epsilon around x is given by a set of all those points V dash in V, such that mod Fv minus V dash is less than epsilon for any f in V star. So let's look at some problems related to weak topology. Question number 4. Let W let V be a Banach space and W be a subspace of V. Part A says that if W is closed, by closed I mean strongly closed. If W is closed, then W weak is basically W intersection V weak. That means any weakly open ball or any open ball with respect to weak topology or in W is nothing but some in some form of W intersection, some open ball in W intersection, some weakly open ball in V. Because eventually open sets are arbitrary union and finite intersection of open balls. Let B V epsilon be an open ball in W, W, but W weak. That means this is a ball with respect to weak topology. So this implies B V epsilon is set of all those points V dash or let's write it as W dash such that mod f W minus W dash is less than epsilon for some f in W star. Now by Hahn-Banach theorem, for this f, I can find its extension in V star. So I can write it as W intersection all those points V dash in V such that mod f tilde W minus V dash is less than epsilon. Is it fine how I did this? Because clearly this f value of f tilde at every point in W is same as that of f, where this f tilde is Hahn-Banach extension of f on V. So now this is a weakly open ball in V. So I can write it as W. This is W intersection B V W epsilon. And since B W epsilon is an arbitrary open ball in W weak, we have W weak is equal to W intersection V weak. I hope this is fine. Let's move towards part B. Show that the strong closure of W is equal to weak closure of W when W is a subspace of V. Solution. Firstly, I claim that W closure is a subset of, strong closure is a subset of weak closure. Now suppose X belongs to strong closure of W. That means there exists a sequence Xn in W such that Xn converges strongly to X in W. And we know that strong convergence implies weak convergence. This implies Xn converges weakly to X in W. Now, since Xn is a sequence in W, this implies X belongs to weak closure of W. Therefore, W strong closure is a subset of W weak closure. Now, since W closure is strongly closed, strongly closed, clearly because this is a closed set, and convex, convexity will get convexity because of the fact that W is subspace. Since for every x, y in W bar, there exists W closure, strong closure, there exists sequence xn and yn in W such that xn converges strongly to x and yn converges strongly to y. This implies txn plus 1 minus tyn converges to tx plus 1 minus ty strongly in W. Now, since this is a sequence in W, this we get tx plus 1 minus ty belongs to W closure for every t belonging to open interval 0 to 1. Therefore, W closure is convex. And we know that strongly convex plus closed implies weakly closed. This implies W bar is weakly closed. This implies weak closure of W closure is equal to W closure. Now, since W is a subset of W closure, this implies W weak closure is a subset of W closure weak closure, which is equal to W closure. This gives us that weak closure is a subset of strong closure. Earlier, we had the other side of relation. Therefore, weak closure is equal to strong closure. So I hope this is fine. Okay, then let's move to next question. Question number 5. Let T be a linear operator in V. Part A. Show that now this implies T from V to V is linear and continuous with respect to the strong topology. When we both domain and codomain are V, with Banach space P with their norm topology. So that T from V to V weak and T from V weak to V weak are continuous. Now we'll see what happens for the case of weak topology. Solution. Firstly, we'll look at T from V weak to V weak. So basically, in order to show that this is continuous, we need to show that every open ball in V weak, that means where every weakly open ball in V has a pre-image, which is its pre-image should also be weakly open in V. So instead of open set, I'll consider open ball. Let U be an open ball in V weak. So obviously, U is some ball around a point V which is in range T. This implies there exists V in range T such that U is just epsilon ball around V. This is equal to set of all those points in V such that Fv minus V prime is less than epsilon. Now since V belongs to range T, this implies there exists some V bar in V such that V is equal to TV bar. This implies U is equal to set of all those points V prime in V such that mod F TV bar minus V prime is less than epsilon. So this implies T inverse U is set of all those points V prime in V such that mod F T at V bar minus F T at V prime. This is less than epsilon. And since Ft belongs to V star, this implies T inverse U is a weakly open ball in in V. That means, or T inverse U is open in V weak. This gives us T from V weak to V weak is continuous. Now consider the identity map from V to V weak. So basically, this is just identity map, the domain with strong topology and codomain with weak topology. So let U be an open set in V weak. This implies since every weakly open set is strongly open as well, this implies U is open in V, or we can say that identity inverse of U is open in V. This implies this identity map is continuous. This implies T composed with identity is also continuous, where this T was from V weak to V weak. We have shown earlier that this T is continuous, so the composition of this T with identity map will also be continuous. Now this T composed with identity map is from V to V weak. Yes, continuous. Okay, let's move to second part B. We need to show that T from weak topology to strong topology need not be continuous. Taking T to be. So if we give one example of such T from V weak to V, which is not continuous, will be done. So I'll take T to be identity. Let T is equal to identity map from V weak to V. Now since every strongly open ball need not be weakly open, that's how weak topology is actually defined. Weak topology is a smaller topology. So there are some sets, some open sets in strong topology which are not in weak. Since every open set in strong topology need not be weakly open, this implies there exists a subset U of V such that U is strongly open but not weakly. This implies identity, or we can write T inverse. T inverse of this U is not open in V weak. This implies T is not continuous. I hope this is fine. Let's move to next question. Question number 6. Let V be a Banach space and T from V to V be linear. First part. If T from strong to weak topology is continuous, then T bar is actually equal to T. Just in order to differentiate the two functions, two operators, I'll representing it by T bar from strong to strong is continuous. Now let F belonging to the dual of V star be arbitrary. This implies F from V weak to R is continuous. In fact, this is how weak topology is defined. Weak topology is the smallest topology such that every functional is continuous. Since for every xn converging weakly to x in V, fxn converges strongly to fx in R. This implies F composed with T, which is from V to R, is continuous for every F in V star. Now I claim that T bar is continuous. We'll be basically mainly using the uniform boundedness principle in order to show this. So we all know that continuous map, if T is linear, then it maps bounded sets to bounded set. So let B be a bounded set at in V. Now for every x in B, define Jx from V star to R, Jx at any point G is equal to G at T bar x for every G in V star. So this implies mod Jxg, which is equal to G at T bar x, which is basically G at Tx itself, because T and T bar are same, just with different topologies. This is less than equal to norm G and Tx is an element in V. Again, since T is linear and continuous, we are given that this T is continuous. So this is less than equal to norm T, norm X, which is less than equal to some M depending on X. Right? I can write it less than equal to M G, since Tx, x belonging to B, is bounded in V weak, because T from V to V weak is continuous. That is what we are given. And G from V weak to R is continuous. This implies the set GTX, x belonging to B, is bounded. It's just that the upper bound will depend on G. Therefore, supremum x in B mod JXG is finite for every G in V star. Now, since we are in the Banach space setup, we can use the uniform boundedness principle. This implies by uniform boundedness principle, there exists some m bar positive such that supremum x in B norm Jx is less than equal to m bar. And since Jx is nothing but evaluation map at T bar x, so this implies supremum x in B norm T bar x is less than equal to m bar, because norm Jx is equal to norm T bar x. This implies T bar B is bounded. Hence, T bar is continuous. I hope this proof is fine with everyone. Then let's move to next part. If T from V weak to V weak is continuous, then T bar from V to V is continuous, where T bar is just T. Only difference is the topology. Now, for any F in V star, F belonging to V star be arbitrary. Again, by definition of a weak topology, we know that F from V weak to R is continuous. This implies F composed with T from V weak to R is continuous. And we have done earlier that the identity map from V to V weak, we had seen earlier, na? Identity from V to V weak is always continuous. is continuous. This implies F composed with T composed with identity is continuous for every F in V star, and T composed with identity is from V to V weak, and T is from V weak to V weak. From V to V weak. And we have a result. You can prove this using the same method, the way we have used the uniform boundedness principle in the previous question. With that, we can show that T is continuous if and only if F composed with T is continuous for every F in V star. So now, since F composed with T or identity is continuous for every F in V star, this implies T composed with identity from V to V weak is continuous, and hence by part 1, T bar from V to V is continuous. That is what we had to prove. I hope this is fine. Let's move to next part. If T from V weak to V is continuous, then also T bar from V to V is continuous. Where again T bar is equal to T. So you can see that if either the domain or range or both we take with respect to weak topology, and in that case the function is continuous, then we get our linear function to be continuous as well. Now since identity map from V to V weak is continuous, we had proved earlier, this implies T composed with identity is decomposed with identity, and this is from V to V is continuous, and this is basically T bar is continuous. Hence we are done. Now let's look at some weak convergence. Question 7. Let En be the sequence that has 1 at nth position and 0 elsewhere. Position. Show that En converges weakly to 0 in C naught, where C naught is the space of sequences converging to 0. And in this space, our norm is the sup norm. And also we know that C naught star is L1. Solution. So in order to show that En converges weakly to 0, we need to show that Fen converges strongly to 0 for every F in C naught star. And here C naught star is L1. So let F belonging to C naught star, which is equal to L1, be arbitrary. This implies there exists a Y in L1 such that f of x is equal to summation k from 1 to infinity xk yk for every x equal to x1, x2, so on in C naught. This implies Fen. Now, since En has all terms 0 except for k equals to n, so the sum will be sum, and the nth term is 1, so this is just yn. Every n in n. Now, since yn is a sequence in L1, this implies the sum is finite and hence it converges to 0. This implies Fen converges to 0 as n tends to infinity. And since f belonging to C naught star is arbitrary, we get En converges weakly to 0 in C naught. From here, we can see that En can never converge because suppose if it converges, then the only possibility would be 0. And if En converges strongly to 0, then for epsilon positive, there exists some n naught in n such that the sup norm of En is less than epsilon for all n greater than equal to n. But the sup norm is 1 for every n. So this will not hold if I take epsilon to be strictly less than 1. So therefore, we get En never converges. I hope this solution is fine. Okay, then let's move to the next question, the last question for this session. Question number 8. Let xn converges weakly to x and norm xn is less than equal to norm x for every n and n. Then show that the sequence norm xn converges to norm x. Solution. So we have xn converges weakly to x, and norm xn is less than or equal to norm x for every n in n. Suppose norm xn does not converge to norm x. Now, since this is a bounded sequence in R, obviously it has a convergent subsequence. Moreover, we are saying that it is not converging to norm x. In that case, we can find a subsequence that converges to some y which is strictly less than norm x. This implies there exists a subsequence xnk of xn such that xnk converges to some y which is strictly less than norm x. Now, by Hand-Banach theorem, we can find a functional f in V star with norm f equals to 1 such that it attains norm x, such that f of x is equal to norm x. Now this implies f of x minus fxnk, this is greater than equal to norm x minus norm xnk. Why? Because norm x is equal to fx, and modulus of fx and fxnk is less than equal to mod fxnk, which is less than equal to norm f, norm xnk, and norm f is equal to 1. So this is equal to norm xnk, and which gives us minus fxnk is greater than equal to minus norm xnk, which is greater than equal to norm x minus y, because norm xnk converges to y. This implies for every epsilon positive, there exists some k naught in n such that minus epsilon plus y is strictly less than norm xnk is less than epsilon plus y for every k greater than equal to k naught. And since epsilon positive is arbitrary, we get norm xnk less than equal to y. So this happens as k tends to infinity. And this is strictly positive because we had taken y to be strictly less than norm x as k tends to infinity. So this implies mod fx minus fxnk is strictly positive as k tends to infinity. But since we had weak convergence and f belongs to V star, this fx minus fxnk should be equal to 0 as k tends to infinity. Now that gives us a contradiction. Therefore, by contradiction, norm xn should converge to norm x. This is norm xnk. So I hope this solution is fine. So if you have any doubt, please let me know. So if not, we can uh, finish this session. Okay, then we'll meet next Friday. Thank you.